Hi guys, sorry, the video got cut off after 15 minutes. So as I was saying, this is just an analogy to show you how the resistance in a wire compares to water being produced or flowing in a through resistance created by these different varying sizes of pipes. Okay, and so longer, thinner pipes have more resistance to the flow of water than pipes with a larger diameter. So in this, the same idea applies in electricity. So the more resistance that you have in a circuit, the more it will decrease current at a given potential difference. So again, resistance, to summarize again, is measured in ohms. The symbol that is given is this Greek letter, which is the omega letter, and it's electrical resistance, which is signified by that the letter R, is defined as the ratio of potential difference across the load, which is V, to the current through the load, which is I. So resistance equals potential difference over current, but the resistance, this relationship is usually written where you've got potential difference is equal to IR, or current and resistance. So sometimes when we talked about this before, where you have a very simple electric circuit where you have a battery or a cell, and then you have conducting wires and no other form of resistance. So electrons are really lazy. They'll take the path of least resistance. So if they're allowed to flow through an electric circuit without a load, they basically will return to that cell, to the opposite terminal of that cell, without losing any voltage. And this basically causes what is known as a short circuit. It's dangerous, and you can start a fire within that circuit, because there's nothing that's slowing down those electrons and reducing their potential energy. So this is a short circuit, and there are fuses that are, as you remember, fuses that are placed within circuits to prevent this from happening. So this table basically goes over the factors affecting the resistance of a wire, and understanding these four characteristics and their effect on the conducting wires basically allows engineers to design very efficient resistors and conductors when they are making up different types of technology. So length, cross-sectional area, temperature, material or conductivity are all factors that affect the resistance of these wires. I'm going to go through, you can look at this by yourself, but I'm going to go through each of these with a little bit more of an example. So material, obviously the material is a factor that affects the resistance. So silver, for example, has the least resistance in terms of metals that are used, but silver is very expensive to use as a resistor within electrical circuits, like everyday electrical circuits. So most of the conducting wires that are used within electrical circuits are made up of copper, okay, which is still a good amount of resistance, but not as good as silver. But it's a cost thing. Temperature. So as the temperature of a wire increases, its resistance also increases, where the conductivity decreases. So that makes sense. So if you increase the resistance, you're slowing down the flow, and therefore you're decreasing conductivity, which is allowing conductors allow for electrons to move freely, but it becomes less conductive as you increase the temperature of that material, of that metal, for example. So in other words, a colder wire is less resistant than a warmer wire. The length is another factor. So the longer the wire, the more resistance it offers than compared to shorter wires. So if the wire doubles in length, basically the resistance is also doubled, which also makes sense. Cross-sectional area, wider wires will offer less resistance. Remember that analogy with the pipes and let me just go back to that quickly. Here we go. So the wider the diameter, the more of your the less resistance. The narrower the diameter, the more resistance. Oops, I'm going backward. Oops, okay. So if the wire doubles in width, its resistance is half as great. Conducting wires that carry large currents need large diameters to lessen their resistance. Okay, so when you get a thicker and thicker wires, you're going to have more copper wires together that are placed together. You can't just have one big fat one. For example, so designing circuit materials, this is so both a power cable of an electric stove and a power cord of an electric kettle, they both use wires that are made up of copper. However, one very large copper wire could make a power cable very stiff. So, you can't have a big fat, even though you need to have more copper for a power cable compared to an electric kettle. You can't just have a thicker piece of copper because it's not going to be flexible. It's going to be very stiff and therefore not very useful to use as a conducting wire. So to reduce the resistance of the conductor while increasing the flexibility, modern power cables are made up of many small diameter copper wires that are just kind of put together. So you can see around these, this is a much thicker, a wider diameter cable, and it's made up of multiple like smaller cables in there, and then each of those is made up of multiple copper wires that are just kind of placed together, and it's not just one big fat thick copper wire, it's multiple thin ones, which make it a better design. So again, Ohm's law is the potential difference between 2 points on a conductor, and this is basically proportional, directly related to the electric current flowing through the conductor. So V is equal to IR. This is the relationship. It's commonly written as this, Ohm's law, whereas V is equal to electrical potential, or the voltage drop, represented by V. I is electric current, represented by A. And R is equal to electrical resistance, represented by the omega symbol there. Okay, it's ohm. So you can also rearrange those equations to figure out what is required if you're looking at different problems. So what I usually do is, it's called the thumb rule. Whatever you're trying to figure out, whether it's resistance, like if you're trying to figure out resistance, use this triangle. You just memorize this triangle. Well, it's so easy to memorize any of these. If you memorize one, you can figure out how to get the other by process of elimination, I guess. But what I've told other students is that you just cover the variable that you're trying to figure out with your thumb. So you want to figure out what the resistance is. You put your thumb on the R and you figure out that resistance is equal to V over I. You want to figure out what voltage is. You put your thumb on the V, and voltage is going to be equal to I times R. Okay? And you can figure out that very easily. I'm sure you guys are smart. So what is the question number one? So there's going to be a lot of problem solving now for the next couple of lessons. So I want to go over some of these problems with you. So the first one is, what is the voltage drop across the tungsten filament in a 100 watt light bulb? The resistance of the filament is 144 ohm and a current of 0.833 amps is flowing through it. So what are we trying to figure out? We're going to use the GRASS method. I'm just going to put that here. GRASS method, because you're showing all your work that way. So the first thing that we do is we write down what we are given. So we are given this value here and we're given this value over here. So that means we are given the resistance. Oops, what happened to that? Which is 144 ohm. And we are given the current, which is 0.833 amp. Okay, this is the resistance and the current. And I apologize for this writing again. It's very difficult to write when a screen is upright. And so what is required? Required is, sorry, I'm using my husband's computer and there's so many pop-ups. So required is, what is the voltage? What is the voltage drop? So voltage is basically required. And what is going to be the analysis? We are going to use this equation. V is equal to I times R. Okay. Solution, you plug in your values. So it's going to be 0.833 multiplied by the resistance, which is 144. Okay. And this is the value that we get, which is 0.833 times 144 is equal to 100, and basically 100. V is equal to 120 volts. I just rounded it up, okay? And we always include the statement. This last S should be the statement, okay? And the statement is basically the voltage drop across the bulb. I'm just going to write bulb instead of the whole tungsten filament, is 120 volts. Okay, and that's that problem. The last problem that I'm going to do with you is this one. So it's a 9-volt battery, maintains a current of 3 amp, 9-volt battery through a portable radio. What is the resistance? So first of all, what are we given? We are given current again, which is 3 amp. We are given voltage, which is 9 volts. What is required? Well, resistance is required. What is the analysis? R is equal to V over I. And so the solution is plugging in those values. So it's 9 divided by 3, which is 3. So the statement is going to be easily the resistance of the conductor is 3 ohm. Okay, and that is how you do these problems. So I'm going to be posting some practice problems with a whole bunch of these different types to solve different types of these Ohm's law problems. And if you have any questions, concerns, please let me know. Message me privately, and I can set up a Google Meet to go over any of these with you. Okay? And I hope you have a wonderful day. Take care.